Hello. Today we're going to talk about Chapter 25, Comparing Counts. So what if I told you that Pisces, or people who are Pisces, are more likely to be rich, right? Are more likely to be a Fortune 400 executive, right? Sounds crazy, but what would you do to test that theory? Okay. Well, here's a bunch of totals of Fortune 400 executives and what sign they are. And what we would do is called a goodness of fit test. So that tests the distribution of counts in a categorical variable, okay? And we're testing to see if it matches the distribution. And as always, there are assumptions and conditions. The counted data condition means that you are, all the data are counts. How many of whatever. Independence assumption, everything should be independent and random, all that good stuff. Sample size assumption, we have to have enough data for it to work. So in the expected cell frequency condition, okay, you'll get there, should expect at least 5 individuals in each cell. So for the expected counts, we need at least 5 people in each cell. So it's similar to that condition that it must be at least 10. So similar idea there. We just want to make sure we have enough to make it, to get information. So how do we do it? Well, we have our observations. So think about those Fortune 400 executives. We have their distribution, and that's the observed. And then really we want to look at, we want to compare it to what you would expect. So you're looking at differences. Okay, and just like with residuals, okay, the sum would just be 0 if we add them all up. So we square them. Okay, to get an idea of the relative sizes of the differences, we will divide each squared difference by the expected count. Oh, for that cell. All right. So it is called the chi-squared statistic, or chi-square. Okay, so the CHI is chi. It's found by adding them all up, the observed minus expected squared over the expected, okay? It is modeled very similarly to the T distribution, so you use degrees of freedom, okay, because it depends on how many categories essentially you have. So the number of degrees of freedom is just n minus 1. With a chi-square, you get the question one-sided or two-sided. Well, we don't use it for confidence intervals, okay? It's only used for testing hypotheses, whatever. If the observed counts don't match the expected, the statistic will be large, okay? It can't be too small, so that chi-square is always one-sided because of that, okay? Just if the stat's large enough, we'll reject the null. That's what we're looking at. With a chi-squared, it's not as simple as a one-sided alternative hypothesis. It's many-sided. There's lots of ways things can go wrong. So we don't know which direction. Okay, it's not just two-sided. There's too many things to look at. So we just kind of keep it simple. It either is significant or it's not. Okay, we either reject it or we don't. And here is it broken down in simple, what's the word I'm looking for? A simple list. There we go. So you find your expected values. Okay. Every model you're given a hypothesized proportion. Okay. The expected value, you multiply the total number of observations times that proportion. Okay, that's supposed to be expected, right? Like for the Fortune 400 executives, you expect to be 1 out of 12 zodiac signs. So you'd multiply the number of observations in each cell times 1/12. Okay. You then compute the residuals, observed minus expected, you square them, you add them, you divide them by the expected, and then you add them. There's your chi-squared statistic. You take that with your degrees of freedom, and then you test your hypothesis. Okay, you can look at your table, or we can use our calculator. All right. Okay, so what does the model tell us? All right. Usually, when you do a goodness of fit test, that's you have are likely to be performed by people who have a theory of what the proportion should be and who believe their theory to be true. Okay, but the goodness of fit, you can only use the null hypothesis. Okay, so we either, like I said earlier, we either accept it or reject it. I'm sorry, we don't accept, we reject or fail to reject. All right, we can't confirm that the fact is true, okay, or that the theory is true, but all we can say, this is the key here, all we can say is that the data is consistent with the proposed theory. Like, oh, well, yeah, actually, it looks off, but it's not. It's following, what you would expect to happen. Okay, that's all it's saying. All right, now what if we wanted to test the distribution against two or more groups, okay, against the same category, okay? That's a chi-square test of homogeneity. I always say that weird. Homogeneity. Anyway, so this test is actually the generalization of the two proportion z test, okay, because you're comparing two or more groups, okay? This statistic that we calculate is identical to the chi-squared statistic for goodness of fit, so it's similar there. Not similar, it's the same. In this test, we ask whether choices are the same among different groups, okay? So there is no model. We're seeing if it's the same against women and men, if it's the same against every race, okay, that kind of thing. There is no model. We just want to see if there's a difference, okay, among the categories, okay, or the groups. The expected counts are found directly from the data, and we have different degrees of freedom. Okay, so we take our data from it. Of course, there's always assumptions and conditions, so luckily these are all the same as the chi-squared goodness of fit. Okay. The counted data condition, the randomization, 10%, as long as we don't want to generalize, we don't have to check those conditions. Okay. The expected count still needs to be at least 5. Now for the expected counts, we multiply the row total by the column total and divide by the grand total. Okay, so that's like think about your contingency table. So you do those totals. Okay, so here you've got your chi-squared statistic, and for your degrees of freedom, you multiply. So the rows minus 1, the columns minus 1, and then multiply those numbers. Okay, so you need your degrees of freedom to find the p-value. So you can't mess up the degrees of freedom or you just mess up everything. Fun, right? Okay, so when we reject the null hypothesis, we got to look at the residuals, right? Residuals are super important. Don't forget them. So just in general, we always talk about them. For a chi-squares test, we want to work with standardized residuals. So, because, residuals for cells may have very different counts, okay? So it's easier to compare the residuals. So to standardize them, you use this. So you divide by the square root of the expected, okay? Now, those residuals, the standardized residuals that we get, the plus or minus indicates whether we observed more cases than expected or fewer. So that's helpful. They give us a chance to think about underlying patterns, just like they did with the linear regressions we did. When you graph those residuals then, right, we could look for patterns. Well, you could look for patterns here when you standardize the residuals. Okay, not just looking at the expected counts, you're looking at the residuals. All right, your contingency tables. So for a test for independence, okay, chi-squared test for independence, you have contingency tables so we can see whether the distribution of counts on one variable is contingent on the other, right? What did the book have? It was talked about your ears, whether they were attached to the neck, and whether or not you could roll your tongue. So that would be like a contingency table, you know, those that can have their ears attached and roll their tongue, or ears attached and not roll their tongue. Not ears attached, roll the tongue, not roll the tongue, right? Remember? Okay. A test of whether the two categorical variables are independent examines the distribution of counts for one group of individuals classified according to both variables in a contingency table. Okay. You're testing two categorical variables against each other. Okay. So, you want to think about how you, which one you're calling it. Is it a test for homogeneity or a test for independence? Okay, you got to look at how the data was collected. If the data are categories of a single variable gathered from more than one group, and we wonder whether the groups are the same, that's homogeneity. When our data cross-categorize two variables gathered from a single group, okay, we wonder whether there's an association, and that's independence. Okay, so make sure you understand the difference, because they're the same calculation, all right, but you want to make sure that you call it the right thing. As always, you have assumptions and conditions. We still need counts and enough data so that the expected values are at least 5 in each cell. If we're interested in the independence of variables, we usually want to generalize from the data to some population. Okay, so you want at least 5 in your expected, and you try to generalize from some population. Okay, and of course represent random sample from that population. And of course you want to look at the residuals again. So each cell contributes a term to the chi-squared sum. So look at the standardized residuals just like we did in the other test. So chi-square tests are pretty common, okay? But we have to remember that the small p-value does not prove causation. Correlation is not causation. So it treats the two variables symmetrically the same. We can't differentiate the difference. We can't differentiate the causes, okay, if there existed any, right? We can't see that effect on everything, okay? We can't eliminate a lurking variable. So you just got to be careful. You know, in some ways, the failure of independence between two categorical variables, it's less impressive than a strong, consistent linear association. Okay, so it's not as confident with this. Okay, I'm not getting into percentages, but it's just not as of a sure thing. Okay, because there could be those lurking variables. So you want to look at your standardized residuals to help you think about underlying patterns. All right, so what can go wrong? Don't use chi-square methods unless you have counts, okay? Only with counts. Just because numbers are in a two-way table doesn't make them suitable for chi-square, okay? So contingency table is not equivalent to chi-square, okay? Beware of large samples. With a sufficiently large sample size, a chi-square test can always reject the null hypothesis. So you don't want to get too large, right? Think about that, just like a 10% condition, right? We never want to go too large, but we also don't want to go too small. So don't say that one variable depends on the other just because they're not independent. Association is not causation, right? We know this. And this is everything we learned. So hopefully this all makes sense. If you have any questions or you want me to go through and show you with the calculator, I'd be happy to. I'll see you in class.